This is the first lecture for Chapter 10, in which we're going to look at sinusoidal steady-state analysis, or in other words, solving circuits that have sources that use alternating current, or AC. This first part, we're going to look at a quick review of phasors, and then we're going to see how to do nodal and mesh analysis on circuits that have AC sources. So you've already seen this table that shows how to switch from a time domain representation to the phasor representation for a sinusoidal signal. We've also already gone over complex numbers, and the important points to remember here are that there is a rectangular notation where you have a real part and an imaginary term, and we can equate this to a phasor representation or a polar notation. If you have it in the rectangular notation, it makes it easy to add and subtract two different complex numbers. And if you have it in the phasor or polar notation, it makes it easy to multiply and divide two different complex numbers. We also would want to switch between both rectangular and polar notation. And we can do that by following the equations in the two boxes on this slide. Just note that in order to convert to the phase angle for the phasor notation from the rectangular notation, it might be necessary to alter that arctangent equation a little bit, depending on what quadrant the complex number vector representation is in, and that is on this slide. So, if it's a real number plus a positive imaginary number, then it's the equation shown on the previous slide. But if you have different combinations, then you will need to change what that equation becomes in order to figure out the phase angle. That complex number representation or phasor representation relates to impedance, which we described in the previous chapter. And this is just a more complex, since it's a complex number, more complex representation of the concept of resistance. So the impedance of a resistor is going to be equal to its resistance, but we can also define the impedance of a capacitor. That's 1 over j omega c, and the impedance of an inductor, which is j omega l. So both the capacitor impedance and the inductor impedance are going to depend on frequency, because they have omega in their impedance representations. And this is going to tell us how these circuit elements will respond to voltages and currents being applied to them. We can then use impedance to be able to reuse all of our DC circuit analysis tools for AC circuits that have resistors, capacitors, and inductors. So let's quickly review some of our DC circuit analysis tools. So two methods that we have covered extensively are nodal analysis and mesh analysis. And these are the steps for each method. For nodal analysis, you set a reference node, identify the non-reference nodes, apply KCL at the non-reference nodes, and then you end up with a set of equations that you can solve for the unknowns. For mesh analysis, you identify the different loops in the circuit, apply KVL to each one of those loops or meshes, and again you end up with a set of equations to solve for a given solve for the same number of unknowns. And we did this many times, but we've only done them so far for DC circuits. What we're going to learn is that we can use these same methods for AC circuits. We just need to convert everything to the phasor form. Then we can solve using the same methods that we did before. We'll end up with a phasor form for the result, and if you wanted to have the time domain format, then we can convert it back at the end once we get the results that we want. So let's look at an example of this. So we have this circuit. There is a capacitor here, a resistor here and here, an inductor here, a dependent voltage source, and there is an AC current source. It's a time-dependent sinusoidal current source. Okay, so how can we solve this circuit? So the first step is going to be convert all of the relevant components in this circuit to their phasor representation. So we're going to convert to the phasor representations for the relevant elements in the circuit. Okay, so which ones are the relevant ones? Well, we have a time varying current, and then we have a capacitor that has an impedance that will depend on the frequency of the signal, and an inductor that also has an impedance, and its impedance depends on the frequency of the signal. Okay, so let's start with our current source, because that's setting the frequency of the AC signal throughout this circuit. So it's cosine of 2t. So we know that the angular frequency omega is equal to 2 radians per second. And this is going to be the frequency of the current and the voltage throughout this circuit. If we then, and so what we're going to do is we're going to convert to phasors. So we're going to lose that frequency information in the phasor form. So we have to just remember that this circuit has a frequency of 2 radians per second. Okay, then we're going to convert the current source to the phasor representation. So the amplitude of the current is 10 amps. We're looking at a cosine function with no phase associated with it. So the phase angle is going to be 0 degrees. And we said that has units of amps. Okay, now let's convert the capacitor to its impedance form. So the capacitor impedance is 1 over j omega c. C is 0.2 farads. Omega is 2 radians per second. So this is going to be 1 over j times 0.4. This will have units of ohms. And then we're going to convert the inductor to the impedance form. The inductor impedance is j omega L. Omega is 2 radians per second. The inductance is 2 henries. So this is going to be j 4 ohms for the inductor impedance. Okay, so in our original circuit, we are now representing this as we're remembering that our frequency is 2 radians per second. We're setting the current source to its phasor representation. We are putting in the impedance of the capacitor and the impedance of the inductor. And now once we're at this point, we can solve this circuit with our same procedures as for DC circuit analysis. Okay, so let's use nodal analysis, since the title of this example is nodal analysis. So first we need to find the reference node. That probably you want to choose as this ground node. And then we need to identify the non-reference nodes. Those are already labeled, V1 and V2. So we're going to do KCL at those non-reference nodes. So for node V1, we can just say we have some current coming in to V1 from that constant currents from that current source, and let's just assume we have currents leaving that node through the other paths. Okay, so the current entering node V1 is the phasor form of that current source. The current going through the 2 ohm resistor is going to be V1 minus 0, because the other side of the resistor is ground, over 2 ohms. And the current going through the capacitor. Now that we made the capacitor into an impedance, it's just like writing the current term if this was a DC circuit. So the voltage across the capacitor is V1 minus V2, and the impedance of the capacitor is 1 over j times 0.4 ohms. Okay, so that's our equation for node V1. I encourage you to try and write your own equation for node V2. So let's say we have a current coming in to V2 from the capacitor branch, and we have currents leaving node V2 through the 2 other branches. I encourage you to try and write that equation by yourself. So pause that video, write the equation by yourself, and then I'm going to write it and you can check it. Okay, so hopefully you paused the video and wrote down your equation. The current entering the node is the current through the capacitor. So it's going to be the same as the last term in the top equation for node V1. And that's going to be equal to the current leaving node V2. The current leaving node V2 through the inductor is going to be V2 over the inductor impedance. And then the current leaving node V2 through the 4 ohm resistor. The voltage drop across the 4 ohm resistor is V2 minus 3Vx, and I divide by that resistance of 4 ohms. Okay, so we have two equations, but we do have three unknowns because we have V1, V2, and Vx. But if you look at how Vx is defined, Vx is the voltage across the 2 ohm resistor. That's the same as V1. So Vx is really equal to V1. And so we do have two equations and two unknowns. So solve these two equations. So then if we solve these two equations using matrix algebra or your calculator, whatever method you choose to do, you already know how to do this math. We will get V1 is equal to 5.7 plus J 9.8 volts, and V2 is 17.9 plus J 27.7 volts. Now we can convert this to the phasor representation. So V1 in phasor form is going to be a magnitude of 11.3 and a phase of 60 degrees. That has units of volts. And V2 is going to be a magnitude of 33 and a phase angle of 57.1 degrees. And that's going to have units of volts as well. Now let's say we want to convert this back to time domain. So let's do this over on the right. Okay, so we need to remember that our frequency that we did all of this at is 2 radians per second. If for some reason the frequency of the current source changes, what we just did is all invalid. We have to resolve it for the new frequency, because if the frequency changes, that means that these impedance values for the capacitor and the inductor also change, which means that this term is incorrect and this term is incorrect in this equation if the frequency changes. But let's just say we set it as operating at a certain frequency, so it's at that frequency. So we can convert V1 back to the time domain representation. If we look at the phasor, it has a magnitude of 11.3. So it's going to be 11.3 times cosine. Don't have to put omega, we can put the value. Cosine omega 2t, and it has a phase angle of 60 degrees, and that has units of volts. V2 it has a magnitude of 33, cosine of omega t plus 57.1 degrees phase angle, and that has units of volts. Okay, so we solved for the nodal voltages V1 and V2 for this circuit. The calculations are different from a DC circuit, but the process is the same, except for the fact that we have to convert into phasor representation at the beginning, and if you want time domain, we had to convert back out of phasor representation at the end. Now let's look at an example that uses mesh analysis. So again, step 1, we need to convert to the phasor representation of the circuit. But as you can see, that's already been done because this current source is in a phasor representation. This voltage source is in a phasor representation. The inductor already has its impedance labeled, and the capacitor already has its impedance labeled. So that helped us set up the problem. The only thing I don't know, and I really don't know because it's not in the textbook where this example is from either, is what frequency this circuit is working at. Because we're starting off with the phasor representation, so it assumes that we knew the frequency, and we are just remembering that information on the side. But we're never actually given what that frequency is, so I don't know what frequency this circuit is working at. I also don't know, what the capacitor value is or what the inductor value is. So from the impedance, I still cannot figure out what frequency this circuit is supposed to be working at. But that's besides the point for now. So let's just solve for this entirely in the phasor representation. Okay, so step 1 already done for us. So step 2. We have to identify the loops in our circuit to do the mesh current analysis around. Let's say that this is going to be current I1. Let's call this current a mesh current I2, and this is going to be mesh current I3. Sorry, my arrows are kind of ugly. Okay, step 2 done. And now we're going to do step 3, which is KVL around those loops. So let's look at loop that contains mesh current I1. Doesn't matter where we're going to start, so let's just start where the tail of this arrow is. So the first element is going to be the capacitor. So the voltage drop across that is going to be I1 times the impedance, which is negative J2 ohms. Then the voltage drop across that resistor, which is going to be I1 times the impedance, which is 8 ohms. And then the voltage drop across the inductor, which is going to be I1 minus I2 times J 4 ohms, and this is KVL, so these all should equal to 0 volts. Now let's do loop I2. Again, we'll start at the end of the arrow. So the first voltage drop across the 6 ohm resistor is going to be I2 minus I3 times 6 ohms. Then it's the voltage drop across the inductor, which is I2 minus I1 times the inductor impedance of J 4 ohms. And then we have a voltage increase through that voltage source that's 50 angle 30 degrees volts. So far these terms are positive because they've been voltage drops. Now I have to have a negative 50 angle 30 degrees. And this is going to be equal to 0 volts. Each one of these terms has units of voltage. Okay, now let's do loop I3. Loop I3, actually I know we can directly write what that current I3 is, because that should be the current from that current source. So I3 is 10 amps with an angle of 0 degrees. Okay, so we have 3 equations and 3 unknowns, I1, I2, and I3. So we can solve these 3 equations. Probably what it makes more sense, the most sense, is to substitute for I3 in the second equation, because we already have a value from the third equation. We have a value for I3, and then we have 2 equations and 2 unknowns, and then we can solve those equations. So if you do the algebra and solve those 2 equations, what you'll be left with is sorry, these currents got deleted. We'll be left with a complex number form for I1, which is going to be 2.5 plus J 5.4 amps, and I2 is going to be 12.1 plus, minus J 2.2 amps. We can convert this from the rectangular notation to the phasor notation. This is going to be 6.0 magnitude with a phase angle of 65.4 degrees. And for I2, the magnitude will be 12.3 amps, and the phase angle will be negative 10.5 degrees. What I cannot do at this point is I cannot convert these phasor representations to time domain, because I don't know what the frequency is. It's not given for this problem. We didn't actually solve for what we're looking for, which was that current I0, but I naught is the same current as our loop current I1. So we just need to explicitly state that. So to summarize, the phasor notation that we've learned allows us to convert any element that depends on frequency in our circuits to the phasor domain representation. And then once we do that, we analyze the circuits. We can analyze the circuits using the same tools we had before, nodal analysis and mesh analysis, what we covered in this lecture, using the same procedure. And then after we're done with that, if we want to go back to the time domain, we can convert from the phasor form back to time domain. So it's not much more difficult to solve AC circuits as it is for DC circuits. We're still following pretty much the same process. The math is a little more tedious, but other than that, we're kind of just reviewing the nodal and mesh analysis that we did before.